Welcome to ePODstemology.
You know what I like a lot more than materialistic things? Knowledge. What is this?
It's a podcast. Hello and welcome to another episode of ePODstemology. I'm your regular host, Dr Mark Fabian. One of the main motivations for this show is to popularize the genuinely new perspectives being utilized by young and emerging scholars and showcase their paradigm-shifting research. There are a few fields of scholarship that embody this agenda more thoroughly than machine learning, a branch of computer science and statistics that promises to dramatically accelerate the pace of scientific discovery, crack open hard questions that have bedeviled humanity for decades, and even crack open our minds in terms of bringing about whole new ways of understanding our world. We are blessed this episode to be joined by the very erudite Dr. Dave Watson from University College London, who is contributing to the machine learning discourse in a thoroughly interdisciplinary and conceptually sophisticated way. David has a rare gift for making this at times arcane or even genuinely mind-boggling field accessible to a general audience, which includes myself. Our discussion hopefully answers questions that you might have about what machine learning is, why deep neural networks are so hot right now, how they are being applied in areas as diverse as gene mapping and video games, and their potentials and perils. I hope I asked the right questions, but if you have any more, please follow us on Twitter and join in the conversation. Without further ado, let's get into it.
ePODstemology.
All right, David Watson, thank you for joining us on ePODstemology.
Thanks so much for having me. Really excited to be here.
So could you tell us a little bit about your quite wide-ranging research agenda?
Sure. So I'm currently a postdoc in the statistics department, or rather the statistical science department. It's got a slightly fancier name at University College London. My research there is broadly sort of in causality, causal machine learning more specifically. But it's been a sort of long, winding road to get here. I did philosophy in undergrad. I was really focused on epistemology, philosophy of science stuff. I did master's and PhD at the Oxford Internet Institute. So I had a philosophy advisor and a computer science second advisor on my DPhil research there. And I was looking at interpretability in machine learning, explainability, which is a bit of a nascent topic the last few years, especially as machine learning models have gotten incredibly complex and hard to manage, but are also being brought into increasingly important and high risk areas. So like healthcare, finance, even criminal justice and national defense, stuff like that. So I was very interested in those issues of explainability. I've gone a bit of a technical direction now in the postdoc work, and in the fall, I'll be joining the computer science department at King's College, actually the informatics department, because they also have fancy names for their departments.
Right. Cool.
Yeah, so working sort of in the very much in the applied machine learning space, but I'm interested always in epistemological foundations and limits of these methods.
Right.
And that has sort of driven a lot of my research in the last few years.
Okay, cool. I noticed that you've published a lot, especially for a postdoc. Can you maybe talk us through like a couple of your highlight papers?
Sure. I'll say that's to a large degree a function of a couple of things. So first of all, between my master's and DPhil, I worked at a bioinformatics lab in London, a job I was like totally not qualified to get. I really lucked out and learned a ton on that job and was very much like embedded in a lab that was doing quite applied work in sort of health and bioinformatics. So awesome learning experience, and also a real sort of trial by fire to the publication process, because these were, people who were doing big studies all the time. I found myself working on those and learning a little bit about how that sort of process works. And then, yeah, I mean, I had my primary advisor in particular, Luciano Floridi, was always encouraging all of his students, masters and DPhil. It's only a graduate program, the OII, so there were no undergrads in that department. He always encouraged us to aim at publication. So like I turned, the master's thesis into a publication. We had other little like reading discussion groups where he was like, okay, now can we cobble this together into a publication? It was really driving that, like every time we did anything. And that was like occasionally challenging or frustrating, but I'm really happy that I had that sort of encouragement going in, because I do think it has made me a more productive researcher for sure.
Mm-hmm.
It makes me feel sort of comfortable and confident starting new projects and managing different projects at once. So yeah, that's kind of the practical realities of how that came to be.
And what are your two favorite papers, or which ones do you think are the most interesting?
I mean, I'm always the most interested in whatever I'm working on right now.
Right. Sure.
But that's sort of how it has to go, right? But I guess of things that have come out, I guess the ones I'll highlight are, did a paper a couple years ago in Minds and Machines called The Rhetoric and Reality of Anthropomorphism in Artificial Intelligence, which is a bit of a mouthful now that I say it out loud. But I liked that paper because it was quite interdisciplinary in the sense that it was a discussion of a few different sort of machine learning methods that are first of all sort of downplaying how anthropomorphic neural networks are, because that's always touted as one of their big advantages, and then sort of saying actually there are these other machine learning methods that are a bit more anthropomorphic than you might realize, and sort of sketching that out and articulating that, and then taking a bit of a turn toward like ethical discussions at the end and saying, but actually this anthropomorphic tendency that we have when we talk about AI can actually be quite deleterious to ethical debates about these technologies. So I like that sort of brought together different interests and aspects of my research. So that was a fun one. And then more recently, there's a paper that was originally a conference paper at UAI, the Uncertainty in Artificial Intelligence conference we did last year. We've refashioned it, expanded it a bit for a journal publication more recently. And that one is called Local Explanations via Necessity and Sufficiency. So LENS is sort of the catchy acronym. That was co-authored with a bunch of colleagues. We had Lee Moore-Gulchin, who's a computer scientist at Oxford, Luciano, my DPhil advisor who I mentioned earlier, and Ankur Tali, who's a researcher at Google Brain. And again, it was sort of an interdisciplinary thing where I really got to talk about the epistemological role of sufficiency and necessity for explanation, which is something I'm really interested in. Explanation, building on work in philosophy of science and what we want and expect of explanations in that realm, but applying it very much to machine learning contexts for interpretability and explainability, which, as I said, are kind of hot topics in the last few years and what I try to focus on in my thesis research. But it obviously had a very applied aspect as well, and the whole sort of latter half of the paper is us implementing a method for computing these necessary and sufficient sets on actual, machine learning classifiers and showing how that can be efficiently done.
Cool. Very cool stuff. All right. So I think we have to get through this question now, which is, so what exactly is machine learning? So
I take a pretty expansive view of what counts as machine learning, a lot more expansive, I think, than perhaps some of my colleagues. And in fact, I'd say I prefer the term statistical learning to machine learning, because I think that maybe more closely tracks what I understand us to be talking about when we talk about this, because it's really just about finding patterns that generalize in data sets. That at its basic core, that's all we're talking about. Now, there's a million different ways to do this. I think the tripartite division of supervised, unsupervised, and reinforcement learning is a really useful division to keep in mind. We are almost always talking about supervised learning in philosophy when we talk about machine learning, a little bit reinforcement learning, especially recently because it's been so successful at certain interesting tasks. We tend to not say a whole bunch about unsupervised learning, which I think is itself kind of interesting, and I'm doing some research on that right now, so it's very top of mind. But broadly, it's all about finding patterns in data that can generalize to new problem instances. That's really the most basic definition I can give of what machine learning is all about. Okay, and then so I'm sure we'll skate around various themes in what machine learning is for a while and kind of flesh out the concept. I myself am very naive about what machine learning is, so I might ask some dumb questions. But what you just described there sounds a lot like, I suppose, what
some definitions of intelligence are that intelligence allows you to adapt to new environments. It also sounds a bit like some definitions of evolution, I guess, which is an algorithmic process. So it's unsurprising that that comes up in the machine learning context. So can you maybe give us some practical examples of machine learning in action that will sort of illustrate how it operates?
Well, I would first of all totally agree with your point that the borders maybe between intelligence and evolution and learning, these are all intricately sort of intertwined concepts. And I think it's no mistake that we tend to talk about them kind of in the same breath a lot of the time. So reinforcement learning in particular has been very inspired by and has gone on to inspire a lot of research in cognitive psych, for instance, because they're dealing with the same sorts of questions and problems. They're tackling it maybe in slightly different ways. You asked for specific examples of machine learning. I mean, we can focus on just some really prominent ones that have gotten a lot of splashy coverage in the last few years. So DeepMind, the Alphabet subsidiary here in London, has made a lot of headlines, and rightfully so, for some really amazing achievements in the last few years. Probably first got on everyone's radar with AlphaGo, so a automated reinforcement learning algorithm in that case that became the world champion player of Go, the ancient Chinese board game. A updated version of that algorithm, AlphaZero, is now the world champion, not just at Go, but also at chess and shogi and a bunch of other so-called perfect information games. So games where all of the relevant information is sort of on the board, which is very different from like poker, for instance, which is not a perfect information game, but where machine learning, again, has made enormous strides in recent years. So those are reinforcement learning algorithms specifically implemented with deep neural networks. That's where a lot of the sort of cutting edge work has been the last few years. More recently, just in 2021, they introduced AlphaFold. So that was a protein structure prediction algorithm, broadly similar architecture in the sense that it's a deep neural network trained with reinforcement learning. But the application case was quite different there. So looking at sort of biomolecular structures and trying to solve, or at least make big advances in a very, very difficult problem, which is predicting these crazy shapes that protein can fold itself into.
Right.
And saving the scientists who work on this a ton of time in sort of steering hypotheses toward more fruitful directions with that. And while I've not looked too closely at what AlphaFold has done, I take it on good authority that it has been a big step change in how researchers in that area are looking at problems like that. So those would be a few sort of top of mind examples of really prominent machine learning algorithms in the last few years. Those are both reinforcement learning. So maybe I should give you a supervised learning example. It's prominent, so like diagnosis stuff.
Okay.
And DeepMind has actually also been involved in some of the leading examples of this. So diabetic retinopathy is basically an imaging problem. So there's a lot of tumor screening stuff. So if we have high res images of, in the former case, an eyeball, and in the latter case, a tumor, the idea is that a well-trained model that has seen thousands or perhaps millions of labeled examples can evaluate the risk that a patient is perhaps in the early stages of either a cancerous tumor or diabetic retinopathy or things of that nature. So those would be instances of supervised learning tasks where you've learned a pattern from input features to labels, in that case, a medical diagnosis.
And then for unsupervised learning, I guess the example that I have seen is a machine learning algorithm playing Super Mario over and over again and coming up with very innovative.
That's reinforcement learning, actually. So there is a reward signal there.
Yeah.
So AlphaZero is also in the same way. So the difference between AlphaGo and AlphaZero is that AlphaGo had a ton of human games as training data. AlphaZero had no human games as training data. It only ever played itself. So alpha
okay.
0 is similar to what you're describing, I think, and they've done similar things for like StarCraft and a bunch of these sort of game environments where the machine only ever plays itself or other sort of artificial agents. And yeah, you can get amazing results that way. But that is a reinforcement learning problem because there's a reward signal.
Yeah, sure.
So the reward signal is going to be either, you know, a victory or points, I guess, in some of these games. So that's a bit different from unsupervised learning. So unsupervised learning is usually defined kind of by negation. It's like what's left after you've defined supervised and reinforcement. Generally, it's a sort of heterogeneous bunch of methods that are all concerned with structure, finding structure one way or another. So a good example would be a clustering algorithm. And you'll see these also in sort of medical contexts. We're very interested in subtyping cancers. Because for lots of reasons, we believe that no two cancers are quite alike. And maybe there are, even for like, you know, breast cancer, let's say, to take a very well-studied example, there are, I believe, 5, I think, pretty widely recognized subtypes of breast cancer that involve very different, you know, prognostic trajectories. But deciding which category a patient fits into, or even how many categories there are at first, is a challenging task. So clustering algorithms are brought in to look at, in this case, like gene expression. And you say, okay, in this pool of undifferentiated data, I'm seeing maybe 5 like major clusters, 5 subgroups are falling out as like the most meaningfully separate. That would be a clustering problem. And that's an unsupervised learning example.
Okay, cool. How is machine learning distinct from artificial intelligence?
So typically the sort of textbook answer is to say that machine learning is a branch of AI. So you'll say that AI is more inclusive because AI will cover like symbolic reasoning, logic programming, things that are sometimes called good old-fashioned AI. So like the early decades, maybe from the 50s or so through until 80s, 90s, perhaps even later, a lot of, I don't want to pretend that these things are mutually exclusive or that there weren't people working on both throughout that entire period, because there were, but I think it is safe to say that the dominant trend in like computer science departments, at least in the US and maybe the UK as well, other places for that matter, the dominant trend for those early decades after the Second World War was very focused on symbolic reasoning. So really trying to hard program like inference rules and stuff.
Right.
It is only in the last 10 to 20 years that there's been a big sort of paradigm shift toward really focusing on machine learning or statistical learning, where we don't try to do this top-down approach of giving the inference rules, but instead go kind of bottom up. So given a big pool of data, can we find patterns that help inform decisions down the line, inform us for sort of generalized reasoning tasks?
Okay.
So AI is both, arguably, right? I mean, your calculator arguably is doing AI, I guess, if you want to be inclusive about it, but it's certainly not doing machine learning.
Oh, right. Okay. That's interesting. Yeah, I remember this really striking public lecture I went to back when I was at the Australian National University by this German guy there, where he was saying that he'd started out in academia doing artificial intelligence research, and then at one point he'd left because he could not come up with a definition of intelligence that he found satisfactory, and certainly not one that he could express formally, like in a mathematical statement. And so he then went off and did private sector work for 10 years. And then he had this idea and he came back on that basis. And his definition of intelligence...
Then he defined intelligence. Is that what brought him back?
Well, yeah, satisfactorily, at least for his research needs. And I mean, this was like several years ago now, so I'm probably not going to remember it accurately, but his definition of intelligence had something to do with being able to learn in order to meet an objective function across variable environments. So I suppose what you said before, like generalized reasoning task. So I'm curious in terms of machine learning applications and artificial intelligence applications, what the nature of this objective function is. So like in evolution, it's like passing on your genes, for example, but then various psychological and physiological systems develop in order to replicate the genes that then might also have their own kind of sub-utility functions. So it seems now that humans have various reward systems that oftentimes incline them not to reproduce because they're, I don't know, too busy having sex while wearing contraceptives, for example. So yeah, I'm curious whether I'm hitting on something there. And I guess one example that I have in mind is, have you seen Blade Runner 2049? The second Blade Runner film?
Although it was on a plane and I was kind of like going in and out of being asleep. So I
right.
might not know all the references, but yes, I have seen the movie, yes.
Okay. So the character Joy in Blade Runner 2049, I think in popular culture is assumed to be an artificial intelligence, but it seems to me like she's actually just quite a sophisticated machine learning algorithm. So she's like a holographic girlfriend, basically. Right. Over time, she adapts her behavior and personality to be the perfect girlfriend, essentially. So it seems like you have a relatively simple objective function there, and you can do reinforcement learning fairly straightforward. But I'm struggling to kind of think of an artificial intelligence that's different to that. But like, have you played the video game Mass Effect?
No, I don't think so.
No? Oh, I think you should, because it's amazing. But anyway,
I don't think I know. What is it?
It's a kind of epic sci-fi adventure, I guess, where so you play the first human Spectre. So there's a kind of intergalactic alliance of various species, kind of like the Star Trek alliance. Yeah. They use these things called Mass Effect relays to get around the galaxy at greater than light speeds. And the Spectres are a kind of James Bond style 00 organization that report only to the Security Council, essentially, and are otherwise laws unto themselves.
Very bureaucratic, but okay.
Yeah. Well, the point is that they're not subject to bureaucracy. So the Security Council has oversight on them, but otherwise they can do whatever they want, including breaking laws and that sort of thing. And then you discover that there's a grave threat to the universe from the Reapers, which are this artificial intelligence species that just want to wipe out the galaxy periodically, or wipe out all organic intelligent life in the galaxy periodically. Mm-hmm. And you need to then kind of organize all the races together to deal with the Reapers. Curiously, the Reapers are inspired by cephalopods, who do have kind of similar cognitive features that some scientists think they could be similar to humans if they were more social.
Right.
And then, but the spaceship that you get around in has an artificial intelligence in it called Edie. And later in the plot, Edie gets a physical body because she like downloads herself into a cyborg type construct. But anyway, if you're not familiar with that, can you is there a popular culture example of an artificial intelligence that you think is very distinctly an artificial intelligence and not just like a machine learning algorithm?
So let me be sure I understand the question. You're saying the difference you're saying is that an artificial intelligence as opposed to a machine learning algorithm would have a lot of like pre-programmed like inferential rules kind of hardwired in, whereas a machine learning algorithm is just going to adapt to its environment, whatever it is. Is that the question?
Maybe I'm talking nonsense. It seems to me like a machine learning algorithm is something like it has a very simple objective function, like produce more widgets, and then figure out the best way to produce more widgets. Whereas I would think an artificial intelligence has a more vague or complex objective function, which is to like flourish. And then
that sounds. Yeah. Let me repose it maybe as a question. Do you think humans have objective functions? Are we maximizing something when we go about our day?
I think we are, but it is a very complex utility function. Yeah,
I'd say it's. I mean, yeah, you could certainly model it that way. It's maybe not one dimensional. I would say that there's a range of different sorts of utilities, if you like, that we value and that we need to sort of balance and trade off. And I think any sufficiently sophisticated I mean, we just say creature, because I think you see a lot of this in the animal kingdom, beyond humans, is going to need to navigate how to balance potentially, competing values and utilities in that way. So with that in mind, you're asking, is there a good example from pop culture? I recently read 2 books, actually, like in quick succession, that were both contemporary British authors talking about AI. So one was Ian McEwan's Machines Like Us. I think it's called Machines Like Us. It might be Machines Like Me, something like that. And then the more recent one was Ishiguro's Clara and the Sun.
Oh yeah.
So I don't know if you've read either of these, but they are both recent and 2 sort of contemporary British authors, like I said, but they're so different in style and in execution. I mean, the for starters, the Ishiguro one is in first person, which I don't know that I'd seen before. A first person AI narrative, that was a new formal gimmick for me. Maybe there's sci-fi writers that have done that before, but I haven't seen it. And I think, just sort of weighing in on the AI parts of it, forget about the sort of literary merits. I enjoyed both books, by the way, I'll say. I found them both to be very fun. But I think I preferred McEwan's vision. And for people who haven't read the book, it's about there's a lot of things that are very fun about it. It's in a fictionalized like alternate world. So it's a lot like this world, but some things have gone different. So like for starters, Alan Turing is alive, and it's like the 90s or 80s or something. And he's still like weighing in on stuff. But it's funny how like historical events kind of happen, like the Falkland Islands War happens and Argentina wins. And that's like very important kind of to the plot for a point. But anyway, all these sorts of little things that are kind of cute. But the main AI character, whose name is Adam, I believe, so it's kind of got the biblical undertone, is a confusing sort of figure, because he wants to be helpful to those around him, the 2 sort of main characters who adopt him, basically. But he makes some weird choices, without giving too much away. He makes some weird choices about how to balance like loving and respecting these people, and some kind of abstract notions of justice that he comes to value and believe in. And I think it's an open question whether the things he ends up doing are right or wrong. They are kind of extreme. I think they are things that most people would not do, but they're certainly not unintelligent. I mean, they are plausible responses to complicated events and circumstances. Whereas Clara and the Sun, Clara kind of just does some stupid things, to be honest. At least that's how I read it. Maybe it's that's an uncharitable reading, but I was sort of shaking my head sometimes, being like, why would any creature, artificial or otherwise, do these things? So those are a couple of sort of contemporary examples I can think of AI in pop culture, if you like. But it's tough to imagine it, because we don't really know what we're talking about when we think about AI interacting with sort of general environments. We tend to operate in these very sort of siloed domains, where we're like, you want to win this game of Go, here's what you need to know, and we can maximize that, because like I said, it's a perfect information game. It's all the information is available on the board. It's dealing with uncertainty, dealing with low probability but high impact events. That's a much more challenging task. And for evidence of that, look no further than the fact that we still don't really have self-driving cars.
Sure.
And that's something that's like been on the to-do list for I don't even know how many years. And people are always saying, oh, we're about to get it, but I don't know when exactly it's coming out. I'm sure it will. But clearly it's a much more challenging task than a lot of people realized. And I think the reason is because it is so not a perfect information game. It is so full of little complexities and nuances and difficulties that I think we'll be ironing that one out for a long time yet.
Right. Okay. Yeah, really interesting stuff. One more key term to define is, so what is a neural network, and how is a neural network or a deep neural network different from what was done before that?
So a neural network is a class of functions, a very popular one these days, really kind of the dominant mode of a lot of contemporary machine learning. And the basic idea of the neural network is, in its original conception, which was the perceptron, which this guy Rosenblatt, I forget his first name, first advanced in like the 50s, was to base it was very explicitly based on a model of how they thought signals are sent in the human brain. So that's the neural connection. And basically you have all these inputs, which are your features, and they map to a set of neurons, which are like internal nodes through a series of activation functions, which is basically trying to capture the idea that a neuron either fires or doesn't fire. That's the basic kind of intuition. Now you can make a multi-layered perceptron or a deep neural network by stacking these internal layers, so having neurons talking to neurons talking to neurons, all mapping through these nonlinear functions. And the idea is that you get more expressive power when you allow for greater sort of I think of it as kind of ways of twisting space, actually, but that's maybe getting a bit off topic for a second. But your input space, let's say we're looking at a classification problem. You want to separate X's from O's, and you look at your input space, and the X's and O's are kind of all over the place. They're all on top of each other. There's no obvious way to just draw a line that would separate them. Well, what you want to do is kind of twist and pull the space in just such a way that my X's all end up over here and my O's all end up over here. And now a straight line would split them just fine in this new space.
Yeah.
So the internal nodes are basically learning a way to warp the space so that the decision problem becomes simpler. That's one way to think of it.
Oh, okay.
So a neural network is a learning procedure of sort of recursive linearities and nonlinearities through all these sort of internal nodes that ends up spitting out to an output prediction at the end. And if the model has done a good job, it will learn a representation in the internal nodes. And that representation is some way of twisting that space so that the problem suddenly becomes easy.
Yeah, right.
And now we can just say right here, that's the way to do it.
Okay, super cool. That's really interesting. Thanks for that. I like that space twisting metaphor. That made that very intuitive.
A lot of methods kind of do that. So like kernel methods, which were the big machine learning thing for a long time in the run up to neural networks kind of taking over again. Neural networks have been going in and out of fashion for a long time.
All right.
But there was a lot of work, I guess, from like the late 90s. So like Vapnik and a group at Bell Labs started doing work in support vector machines and kernel methods. And it's a very similar logic is going on. What a kernel is a way to twist a space basically in such a way that a problem becomes easier. But the expressive power of kernels is maybe not quite the same. You need to tune certain parameters in a different way. Neural networks can do this in a much more automated fashion, basically. I'm oversimplifying a bit, but that's broadly the difference between these sorts of things.
Okay. Well, speaking of tuning, so my next question is, what does it mean to train an algorithm?
So, I mean, specifically, it depends on the function class. So, this, it means one thing to train a neural network. It means another thing to train whatever, an SVM, to take a kernel example. But, broadly, all of these, a particular instance of a function class. So a function class is just to say all possible neural networks, right? Imagine there was some, space of possible neural networks. If I take a particular neural network, what I've done is assigned particular parameter values to things like how many nodes there are, how many layers there are, what exactly the weights and biases associated with it. I've just specified a bunch of things that are left unspecified in the function class. Training a model just means converging on the right parameters.
Okay.
That's basically how you can think of it. So I start with this incredibly wide world of, all possible neural networks. Well, that's not very useful. I can't really predict anything with that. You can think of this as, to take an evolutionary example, because some of this training is sort of inspired by evolutionary sort of ideas. You can say, well, what if I, try a bunch of random values, see how that does. Okay, well, that didn't do very well at all. Can I take a step, in one direction or another in each parameter space and say, what if I increase this a little bit, decrease this a little bit? Will that do better? If it does better, then I try again, dial it up even more until eventually I settle on a range of parameter values that I don't think I can do much better than. Broadly, that's kind of what training is all about. And that's obviously easier to do with fewer parameters to estimate.
Sure.
But there are quite efficient procedures for optimizing parameters in certain function classes. And this is what made neural networks actually go from being sort of a historical curiosity to a really practical method, is that around 2012, 2013, we started developing very efficient ways to train them. So these big sort of GPU architectures with backpropagation. And it turns out that this thing that, sounded great in principle, but you couldn't really do much with in practice, suddenly became an incredibly effective and practical reality. You could actually train these massive models in a reasonable amount of time and get fantastic results.
Okay. And so can I press you a bit then on, so you mentioned earlier that one of the Go algorithms had a lot of human games to train itself on. And then you just mentioned there you could train an algorithm in a relatively small space of time, or a reasonable amount of time. So how big are the data sets that are required to train an algorithm for various purposes? You could maybe give a few examples, and what are these timeframes that we're talking about?
It depends on a lot of factors. First of all, how long something takes depends totally on your computational resources. If you have massive GPU server farms, then yeah, things can happen a lot more quickly than me on my laptop trying to train a model. But I will say that some of the most exciting and I think interesting advances in machine learning, especially sort of in the deep learning area, are in trying to make training faster. And a really dramatic example actually is the Go example, because AlphaGo was trained on, I think, like 100,000 human games, and then a bunch of self-play after that, and the whole process took weeks, and weeks for a very well-heeled firm plowing a ton of resources at it. So something big was the total price tag and amount of time. AlphaZero, which beat AlphaGo 100 games to nothing in 100 games. So just definitively crushed it. Played way fewer games, like something like a 10th or 100th the number of games, saw no human matches, and was trained in, I think, like 2 days.
Oh, wow.
It was not just better by any sort of measure of performance, but it also was a much more efficient, in the sense of training efficiency, method. And so I think AlphaZero is a much more exciting and interesting development than AlphaGo, honestly. I was not as bowled over by AlphaGo as I think a lot of people were when that happened. I was like, whatever, we've kind of already seen this with chess, we've already seen this with other things. But when AlphaZero came out, I was like, okay, that's actually pretty remarkable that they've managed to beat what was already the world dominant thing totally through self-play, and that much faster. It's like really, really impressive. Image processing is like has kind of been at the forefront of a lot of the latest stuff in AI. And when I say latest, I'm actually kind of being a bit loose here, because that's what sort of started the modern era. So like 2012, 2013, a bunch of convolutional neural networks from like Jeff Hinton's lab became just so much better than the state of the art that everyone kind of had to stop and take notice. And these were trained on massive data sets. So I think the original ImageNet data set that they were using had on the order of like a couple 100,000 images, but that's
Mhm.
before data augmentation. So you can actually augment a training data set in a bunch of ways. So in an image example, you say, this is a picture of a boat. Well, it's
Mhm.
still a picture of a boat if I rotate it 90 degrees, or if I crop it
Right.
differently, or if I change the color, whatever. So every image actually gets whatever, 10, 20 versions
Mhm.
that are perturbed somehow. And I've now, expanded my training data set. So they actually end up having millions of examples to train on.
Right. Okay.
Once they're all done. And how long does it take? I mean, totally depends on the computational resources at your disposal, but we could be looking at days or weeks. I mean, it's not at all uncommon for big tech firms to train models for weeks at a time for like big deployment purposes. That's pretty standard, actually.
Okay. Cool. So my next question then, maybe moving beyond, I was going to ask about sort of some machine learning algorithms in practice, like Netflix's prediction algorithm and stuff like that. But I think it'd be more interesting to get to some of the other questions that I had. So we might just skip that one. What do you see as some of the implications of machine learning for society at large, as opposed to kind of specific applications? Do you have a sense for how big of an impact it's going to make on how we live our lives and that sort of thing?
This is a tricky one because, at the end of the day, it's up to us how much of an impact it will or won't have, right? How we choose to use and regulate these technologies is really the main variable here. That said, it certainly appears that a lot of government investment in machine learning technology has gone toward advancing weaponry and surveillance. Those
Right.
seem to be two really big priorities. DARPA in the United States, which did, to its credit, more or less invent the internet, is investing a ton of money into machine learning methods that can help guide like drone weaponry, for instance. And there's actually a big thing when Google, it was a few years back, but a bunch of Google employees walked out and went on strike because they didn't want their technology to be used for these sort of militarized purposes. But I think Google did end up terminating that contract with the Pentagon, but I think wouldn't be surprised they have a bunch of other contracts with the Pentagon. And if they don't, I assure you many other big tech firms do. That's not a problem, finding people willing to take Pentagon money for some machine learning stuff. China, I guess, has really been at the forefront of using facial recognition technology for surveillance purposes, which is not to say that other countries don't do it. They definitely do, and like police forces in addition. So those are some sort of dramatic examples. We could also look at problematic instances in the private sector. There's been a ton of work written on the tendency for machine learning algorithms trained on historically biased data sets, be it in healthcare or finance or criminal justice, where arguably machine learning shouldn't be used at all.
Right.
But any area where outcomes have maybe not been super equitable in the last, let's say, 100 or so years, the danger is that a naive sort of machine learning approach to those problems could just automate those injustices. It's just going to learn what it sees and replicate it, unless you take make an active effort to guide it towards something else. Those concerns are not just hypothetical. There's been really compelling work done, thinking especially in like the healthcare space. Is really interesting paper in Science a couple years back by Obermeyer et al., who's done a lot of work on this, and they basically got a massive data set from a big, I think, health insurance, an unnamed health insurance company in the US, showing how their sort of automated patient recommendation procedure is racially biased and has definitely impacted I believe it was African American communities in particular, with more adverse outcomes on average. So that's like a very tangible example. there are others that could be potentially harder to quantify, harder to get the data on. I don't think a lot of banks are really eager to share their
Sure.
ugly data sets of all the terrible things they've done in the last few decades. But I think it's safe to say that a completely unmitigated let's throw machine learning at it no matter what approach will tend to lock in a lot of the social injustices that we have rightfully identified as problematic and are trying to sort of address in the first instance. And it could also entrench the power, especially of state actors who perhaps have a monopoly on the really most resource intensive and weaponized use of machine learning, as we've seen in at least the US and China, to take prominent examples. But I by no means think they're alone in investing tons of money into this.
Sure. So, I mean, from that answer, you seem to be like the odds of this turning dystopic seem to be pretty high.
I'm not completely pessimistic. I think that listen, it's technology, and the history of technology is the history of us deciding, do we want to use this to kill people or help people? That's basically like what every single technological advance has kind of brought. And sometimes we make the right call. Sometimes we actually do dramatically improve quality of life for huge portions of the human population through technological advancement. I am not a total doomsayer in that respect. I think it's going to take some tough choices, and it's going to take some real daring regulation on the part of powerful actors who may not see it immediately as in their interest to take those steps.
Sure. Right.
But of the sort of to name some sort of optimistic things to look forward to, I think machine learning can really accelerate a lot of scientific discovery, and that could have huge impacts for medical stuff, especially. So genomics is we are really in the Wild West on genomics. We have no idea basically how biomolecular cellular genetics works. We've known about it for approximately 2 seconds.
Right.
We like really we will look back on, if humans are around in a few hundred years to like look back at this era, we will look back on it as the total birth point of like when we started to really reason about this critically. And I think there's no way we're going to take even the tiniest baby steps in the right direction without really intelligent machine learning models that are going to help us prioritize the right genes to focus on, predict protein folding structures like AlphaFold. These are just problems that involve dimensionalities and data sets that the human mind is not designed to comprehend and work with. And we need these sort of massive data sets and complex non-parametric statistical learning models to make any sense of it. So I'm very optimistic on that front. I think that there's a lot of great work to be done in the next few years in that area, next few decades. I mean, it's going to be keeping us busy for a long time.
Okay, cool. Yeah, all right. That was a nice contrast. All right, I'm going to move to my last cluster of questions here. So the show's name is obviously a slight modification on epistemology, and you've done a bunch of work on the philosophy of science and knowledge in relation to computer science and machine learning. So I wanted to get a few insights from you on that. So I guess one question that often used to come up when we were talking about big data, especially in economics, was that a lot of big data and seemingly some machine learning stuff was basically just data mining. So I remember that people would come out with some huge data set of like financial transactions or something like that. They'd run one of these algorithms into it, and then they'd say, oh, we've discovered that there's this kind of relationship or whatever in contagion of financial systems. So Do you think that there is, let me try to come up with a better question. So is there stuff that big data and machine learning can do in terms of generating knowledge and identifying causal effects that other methodologies can't do, or that it has some particular advantage in?
So what I was going to highlight there was what you ended up throwing in as one of those last words, the causal effects, right? So on its face, so it's called empirical risk minimization, which is what we do when we are interested in supervised learning, for instance. Empirical risk just being optimizing for some loss function is by design completely ignorant of causal structure and causal effects. It will prioritize correlation over causation every time. And sometimes we don't care, but most of the time we do, even when we pretend that we don't. So I actually think it will be essential for any scientific applications, and I mean scientific in the broadest sense to include all sort of social scientific use cases as well, obviously, as natural sciences. It'll be essential to combine the flexibility of these machine learning models with the rigor and assumptions that we do when we do causal modeling. And that's where a lot of the work that I've done the last year or two has kind of been focused. I'm now very much doing work in sort of machine learning and causality. And this is the two absolutely can complement each other. You know, there's a lot of function approximation and function estimation that's required when we do causal reasoning, but we need to fit that into a framework where that's part of a picture and not the only picture, right? So can machine learning be used to estimate causal effects? Yes, absolutely. But to make sure we've done it right, we need to apply those machine learning methods under certain structural constraints and assumptions. And so the whole literature on like heterogeneous treatment effects, for instance, which has been quite big in econometrics with like Chernyshevkov and all that, Wager and Athey have also, I don't know if I'm pronouncing her name right, Susan Athey at Stanford. They've been very focused on this for a few years now. And, you know, to oversimplify a bit, what they're basically saying is, let's, you know, construct a graphical model, if you like, a sort of structural model of how we think these variables are interacting. And then for every kind of conditional expectation involved, we can use a machine learning approach to sort of solve that. And so it becomes kind of plug-in estimators for like nuisance functions or something, nuisance parameters. And yeah, that is a very flexible method. It involves certain untestable assumptions. Any causal reasoning does. I think that's a feature, not a bug. Basically, you need to accept that when you're doing causal reasoning. I mean, Imbens, he just won the Nobel Prize, and he's done some work in this area as well. I think with Mulanathan and stuff. You know, we need not limit our function class just to like linear models, which I think economists and econometricians did for a long time.
Yeah,
and linear
still
models are
mostly
great.
do. Yeah,
and I get why. I mean, there's a lot that you can learn with linear modeling, and it is still to this day, you know, chapter one, and rightfully so, of any applied statistics or statistical learning, machine learning set of methods, is to learn exactly what's going on in linear models. But I think it is not that it doesn't take a big leap of faith or imagination to realize that some functional relationships might not be linear. And even those that are linear, you might need some kind of regularization penalty to get a good estimate in a big data set. And that very much takes us immediately into the realms of like optimization and machine learning stuff when you have to add regularization penalties to linear models. So yes, I think that these methods can totally come together. I would caution against the sort of naive application of machine learning where you just think that if I've got a big enough data set and I throw a big enough neural network at it, all answers will fall out for free. That's not right. That's not what they were designed to do. That's not what they do, in fact. But careful modeling along with explicit assumptions, can totally go hand in hand with the flexible non-parametric properties and advantages of machine learning methods. And we've seen this already. It's already becoming, I think, increasingly popular.
Okay, very cool. All right, one last question, just to maybe hopefully a fun one to finish on. Is there something that people misunderstand about machine learning commonly that sort of really annoys you that you'd like to take this opportunity to kind of set the record straight?
Oh man, probably like several things, honestly.
Oh yeah, go for it.
I guess I'll just sort of I'll go back to something that I've written about before, which is that I think we tend to over dramatize and romanticize the power of neural networks in particular. Something about this function class really like captivates the imagination.
Mm-hmm.
And I think it's because they're called neural networks and because it sounds like it has something to do with brains and that just gets people all like worked up. And I think that can be really unproductive and unhelpful, not just because there are fundamental limitations to neural networks, which I think there are, but because there are so many interesting other function classes with other amazing properties. People make this huge deal out of the universal approximation properties of neural networks, but what they don't realize is that like every function class is a universal approximator almost. Like K nearest neighbors, which is a completely boring algorithm from like the 90s that, you know, whatever, it's also a universal approximator. Trees are universal approximators under certain assumptions. Like that is no, you know, trump card of any kind to say that it can universally converge on any kind of function. It's like, right, lots of things can. And it blinds us to other things that I think are really interesting about methods like bagging and boosting, for instance, which I think are some of the most fascinating kind of approaches. And I don't want to get into the technical details of it, but basically they're ensemble methods. So they're ways to kind of combine a bunch of models.
Right.
And I think those sort of ensemble methods are underexplored, first of all, even though there's been tons written about bagging and boosting. I think there's a lot we still don't fully understand about how these methods work and what exactly their limits are. I think there are really kind of interesting, illuminating sort of correspondences between these ensemble methods and the social aspects of intelligence and learning, which I think we completely ignore when we talk about a neural network and we think about a brain. And it's like, right, but a lot of what makes us intelligent is actually through collaboration and you know, building on things that we've established as social groups and in institutions. And that is very hard to map onto the work of a single neural network. I think we need some sort of ensemble kind of approaches, and we can do this with neural networks and have, you know, multi-agent systems of neural networks or whatever. I'm not pretending that neural networks have no seat at the table, but I think they tend to drown out the discussion of other approaches that are also super promising and interesting in machine learning.
Great. All right. What a wonderful point to finish on. Well, thanks very much, Dave, for coming on the show. This was a really fascinating conversation, way out of my comfort zone. So I'm very grateful for the opportunity. Yeah, thanks very much.
Well, thank you so much for having me, Mark. I really appreciate it.
ePODstemology.
If you enjoyed today's discussion, do check out ePODstemology's page at your favorite podcast directory for more episodes on topics as diverse as tax policy and the meaning of life.